Thanks, Sam. Well, first of all, thanks very much to the organisers for just a fantastic conference. It's really good. I wish Jean-Marc happy birthday when he returns.
Oh, here he is.
Happy birthday.
Thank you.
So we've heard today, the first three talks are all about waves on vorticity fronts, really, on interfaces between a region of constant vorticity and a region of zero flow, I think, in every case. So this is another example. This is an example in a different context and something that can arise in coastal flows. It's joint work with Rob McDonald and two excellent research students, Ollie Southwick and Sean Jamshidi at UCL. So here's some motivation. This is looking down on the Hudson River coming out of New York. It's a sea surface temperature plot. Well, that's what most of the plot is. And so what it shows you is that there's a coastal flow going southwards down here, confined to the coast. The fluid's coming out of here. It's the river discharge. It's warmer, and at least some of it drains off down to the south, and some of it may stay around here. Most outflows, if you look around the world, turn to the right in the northern hemisphere. And so you'd say, well, it's probably a Coriolis effect. Here's one. This is a classic experiment. It wasn't meant to be an experiment. They removed a hydroelectric dam on a river on the Olympic Peninsula, and then it sent out all this silt out here, and it also moves nicely around to the right. Some things to notice is it's pinched in at the upstream edge here, and then it curves smoothly around out here. I'm going to try and argue that that's due to the vorticity dynamics. We don't know what the prevailing currents were. It could just be that the currents moved it around, but it looks reasonably calm. People have done experiments on this. Here we're looking down on a rotating tank. So this tank is rotating. It's rotating in a positive direction. So it's rotating anti-clockwise. We're in the frame of the tank. So the camera is rotating at the same speed. So we just see there's a source here. It's actually a sponge into which they pump dyed light fluid. And it's in the fluid that leaks out of the sponge. The sponge is actually quite small. It forms a blob, and then that blob drains along this way with, in particular, notice it drains with the wall to its right. Drains the wall to its right. It's approximately constant width for a certain distance, and then it rarefies, it becomes thinner. And they notice that the vorticity is negative relative vorticity. In fact, it's almost got zero absolute vorticity. So this is negative relative vorticity. So in here, the fluid is going clockwise. Later on, some people did some numerical simulations of this. They ran an ocean model for this case, and this is what they simulate. Here's the blob, which is the negative relative vorticity, draining along the wall with a constant width, say up to a certain point, and then a rarefaction from that onwards. Okay, so what are the dynamics in this? So the dynamics, we have two waves and we've got image vorticity. So one of the waves is the Kelvin wave. The Kelvin wave's nothing more, in this case, they've got two different densities, so it's an interfacial wave. It's nothing more than a gravity wave. It travels a long gravity wave, travels at the long gravity wave speed, which is modified slightly because the density is not water and air, it's just two layers of fluid. And the only effect of rotation on the Kelvin wave is that it decays away from the wall. And it decays away from the wall over a distance of order the Rossby radius, which is the speed of the wave divided by the rotation rate. And it's the only effect of rotation. It's an interfacial wave, and it depends on vertical displacement of the interface. And it's a unidirectional wave, and it propagates with the wall to its right. There's another wave in the problem. If we've got a jump in the vorticity, then we've got a Rossby wave. A Rossby wave doesn't have necessarily any vertical signature. All it requires is a horizontal displacement. It requires a horizontal velocity gradient or a horizontal velocity vorticity jump. Its speed is proportional to this jump, and it's unidirectional as well, but it's unidirectional such that the high vorticity always is to its right. So the Kelvin wave has the wall to its right, and the Rossby wave always has the high vorticity to its right. And then the final mechanism, of course, is image vorticity. If we've got vorticity near a wall, then it sees an image in the wall, and that image drives the flow. So we've got three things here that can drive this flow. Oops. Well, what equations? It's very interesting what happened there. What equations are we going to use for this? Well, we'll use the shallow water equations. We're going to have one active layer at the top, governed by these shallow water equations, and then an infinitely deep inactive layer below it. And we'll look at the dynamics of the interface between this upper, less dense water and this infinitely deep, dense water. Oops. So here are our governing equations. This is the full shallow water equations. I guess it's just we've got rotation, so I've got the Coriolis force in. And then the classic result for shallow water is that if we cross differentiate, we find that the conserved quantity, it's not quite the vorticity like in the Euler equations. It's of course the so-called potential vorticity, which is the absolute vorticity divided by the thickness of the layer. And zeta here is the relative vorticity. There are two classic limits of these equations. The first limit is this quasi-geostrophic limit, where we assume that the relative vorticity is small compared to the background vorticity. And that's equivalent to saying that so-called Rossby number of the flow is small. And that knocks out the nonlinear terms in the momentum equations. The alternative one that I won't talk about today is the semi-geostrophic equations, and that's to assume that the flow is very long in one dimension, the dimension along the coast, and narrow across, and that's, we don't have to make any assumption then about the Rossby number. We can look at finite Rossby number, and that knocks out the red terms here, but it leaves in these orange terms. And they are, in fact, these are two totally different, really, approximations. The advantage of the semi-geostrophic is it keeps the Kelvin wave. Our QG1 is going to make the Kelvin wave travel infinitely fast. There will be a sine of the Kelvin wave, but it travels infinitely fast. In fact, the solutions are very similar, and they're much easier to find for QG. So we look at two geometries. This is probably what you're seeing in most outflows. We have a shallow outflow. Our river is flowing out into the sea. We're going to take, here's our quiescent deep layer of dense fluid, density ρ2. We're pumping out fluid of density ρ1. And for the QG, we've got to assume that there's an ambient layer of approximately the same thickness lying outside that. So we've got this fluid that we're pumping out. As it's pumped out, it stretches, and as it stretches, it generates positive relative vorticity, or equivalently, by conserving potential vorticity, if H increases, zeta must increase. Moreover, we'll take that each element that comes out stretches the same amount to order one, and so that each piece of fluid will generate the same amount of positive relative vorticity. So we'll have a region here of constant relative vorticity, and then a region of zero relative vorticity outside it. And all the dynamics will be encapsulated actually by the interface. The flow is sufficiently slow that the crude number for the surface is effectively zero. And so we can take the free surface to be rigid. The other case we'll consider is this case, which would say is much less likely for the coast, but that is that we'll assume there's some form of sill here that can hold back the dense fluid so that when the light fluid comes out, it's forced to compress. So it compresses, it generates negative relative vorticity. And so we have a region of negative relative vorticity, or we have our region of zero relative vorticity. So that's probably more unlikely in real life, though some people claim they've found places where the rivers turn to the left. But it's what they do in the experiments. This is precisely what they're doing in the experiments. This is the negative relative vorticity case. So this case is more relevant for experiments. The previous one is probably more relevant for ocean flows. Now we've decided that we're looking down on this. This is a plan of the flow so that all the fluid that's come out of the outflow has got unit vorticity. If we scale correctly, all the fluid out here in this layer has zero vorticity. So we've got the only thing that really matters is the boundary between the fluid that we've expelled and the ambient fluid. So if we can follow that boundary, then we can follow the entire motion because we just color in everything in here as unit vorticity and outside as zero. So that I'll call that boundary C. And in particular, if we look in the long wave limit, it's just some function y of x and t, and that'll be a single valued function in the long wave limit. So what are the governing equations? Well, we've thrown out the nonlinear terms of the momentum equations. So these are the momentum equations. And of course, they just say that the interface displacement is a stream function for the flow. So the interface displacement gives a stream function. The governing equation, conservation of vorticity, is potential vorticity just becomes the potential vorticity is equal to a constant in D, which is either plus or minus 1, zero outside D. It differs slightly from the density, the vorticity you'd see in the Euler equations, which is of course del squared of the stream function. There's an extra term because the interface can stretch and that can generate vorticity as well. So this is the interfacial stretching term. What's the parameter A here? We've scaled all distances on the area flux divided by the vorticity. The square root of that gives us a length, the vortical length. Then A is the ratio of that Rossby radius we had to this vortical length. So it's a measure of the strength either of gravity or the strength of the density contrast. In particular, if you let A go to infinity, that interface becomes rigid, and then we get no generation of vorticity by stretching, only the vorticity we pushed out, and then we get the Euler equations. So it reduces to the Euler equations in the limit of a rigid interface, A equals infinity. What are the boundary conditions? Well, we're just going to specify the normal flow on the boundary. V on the boundary, it's going to be zero outside some source region of width W, and it'll be Q dashed within W. But of course, V is just eta x, so we can integrate that up. You get eta is Q of x, some specified function on the wall. And here's the only place that the Kelvin wave appears. There's an arbitrary constant when we integrate this up. Kelvin wave, we know, can only propagate to the right. So therefore, no disturbance can come from the left. So to the left of the source, Q must be 0. And to the right of the source, Q must be 1. So that's the only sign we have of the Kelvin wave. But it's an important one because it forces the flow in the absence of vorticity to turn to the right. Nothing happens at infinity. And so now we've just, at each instant, we know the boundary conditions on the stream function, and we know the value of the stream function because it's just that domain D. So we can invert that, we get the velocity field and use that to move the flow forwards in time. And this method is known as contour dynamics, a classical method in the Euler equations, but it works just as well for these equations, QG equations. What can we say about the vorticity dominated flow? So let's let A go to infinity. So we've made the interface rigid. The only thing that's driving the flow is the image vorticity. The equation is Laplace's equation. You can solve it, as Darren mentioned, for a point source. And in fact, you could solve it, you map it to the hodograph plane, and you can write down an analytical solution for the shape of this boundary, this steady flow. And here's a comparison. The dotted solution is that solution we just described from the hodograph plane. Dotted solution here, and this is the initial value problem. We've started a source off at the origin. We've got this blob of fluid come out. It starts to move off to the right because we're shooting out positive vorticity. There's negative vorticity here, which is clockwise, which is pushing this to the right, pushes it off to the right. Here's the initial blob getting pushed away, and it's left behind with a solution which is approaching the steady solution. You can see that there are long waves on the surface. These are Rossby waves. In fact, because this is positive relative vorticity, these Rossby waves are being generated here at the stagnation point at the front, and then they're propagating along the front to the right. So we've got waves, long waves propagating to the right along here, long interfacial waves between vorticity step. So now what theory can we do? Well, let's look at a long wave theory. And so we'll do a long wave theory. We'll assume that the waves are long compared to the width of the current. We get the standard interface condition, which just gives us a first order ODE, a PDE. Here is our governing equation. If we only go to leading order, then it's simply X, it's only a PDE in Y, X and T just appear parametrically. So we could just solve this. We could just write down the solution of that, and then we substitute it back into this equation. We've got a first order PDE for the evolution of the flow. And that's known as hydraulics theory. And if we use a uniform source, we can actually solve that problem analytically, explicitly. And this is a solution for positive PVA, positive expelled vorticity for a value of A equals 1. They're all approximately the same. So we can see these are three different subsequent times. The blob starts to move out, and a rarefaction occurs at the front and leading to the right. Grows, the rarefaction grows until it gets to a maximum value here, and then we get a constant width current and a rarefaction. The flow is actually controlled here. In other words, the interfacial wave has speed 0 here, and then this is a controlled flow that sets itself up across the source region, and then this propagating flow to the right. If we increase the vorticity by making A larger, then what we find is that the flow here, the vorticity is sufficiently strong to cause this to overturn, and a shock appears at some finite time, and there's a shock here. So the only difference here is that the rarefaction terminates in a shock. The shock is of finite height at infinity. If we make the vorticity even stronger, then in fact the shock eventually is a full height shock, and the flow propagates to the right, led by a full height shock. And in fact, of course, A equals infinity was the one we were looking at from contour dynamics, and that one has the shock almost instantly, and that was led by pretty well a vertical wall. And here's a comparison between those hydraulic solutions and the contour dynamics run for those particular values of A. for a point source. So this is actually a pretty tough comparison, because the theory was derived assuming the source was wide compared to the width of the current, and we're comparing with numerics for a source of 0 width compared to the width of the current. And yet, nevertheless, you could see that the hydraulics for this case, which the hydraulics is red, the contour dynamics is blue, hydraulics captures the contour dynamics quite well. And you can also see the appearance of the Rossby waves. In this case, the Rossby waves being generated here, and they propagate to the right with high vorticity to their right. This more dramatic stuff happens in the negative PVA, because then the vorticity dynamics is opposing the Kelvin wave. The Kelvin wave always goes to the right, but now the image vorticity is trying to push things to the left. So what we got? We've got, again, we get this case here. The flow is actually uncontrolled. There is no steady solution. So this actually just goes off to infinity. It slows down, but it never stops. It's always led by a rarefaction on that side, and a rarefaction which always has a shock on the left. If we strengthen the vorticity, then we do get a controlled flow. The control appears at some finite time, and we get a control appearing here, the rarefaction leaving from the control, and then we get the downstream current. And the only difference, I think, between these two, this is a finite height downstream jump, and this is the full height jump. The comparison here is not as good. It seems okay for the uncontrolled flow, but for this controlled flow, it really hasn't caught the essence of the flow. It's got an approximation, but I'll come back to this.
What are you comparing here?
So this is the hydraulic solution, but for a 0 width instead of a wide flow, and with contour dynamics for a point source. We can try and widen the source to make the comparison better. So this is a source of width 20. And in fact, it's true. It now does, the hydraulics theory does capture this contour dynamics better, but we'll get giant Rossby waves. Of course, the Rossby waves now propagate to the left, because this is -1 here, the vorticity, and 0 here. So the high vorticity is out here now. And so the vorticity, the Rossby waves propagate in this direction. So the Rossby waves are going this way, and the Kelvin wave is going that way. But this shows you that what's going on is something to do with the width. The discrepancy was due, obviously, to the fact that we did a theory for wide sources and applied it to a source of width 0. Because as we make the source wider, the discrepancy really disappears, though it's still there. So what can we do? Well, let's see if we can examine things in a bit more detail. So we'll go back and we'll forget about the source, and we'll just do a Riemann problem. We'll just suppose that we have a coastal current of 2 constant widths. Y is minus when X is negative, Y plus. So we've got a step, and we just do the classic Riemann problem, let it go and see how it evolves. Moreover, the width of the source seems important. So let's bring in the dispersive terms by expanding everything to 1 term higher in the small parameter, in the width parameter. So here is actually these first terms are the hydraulic theory we were just discussing, but now we get these new dispersive terms. So these terms should bring in waves, and that maybe they'll help us get some better comparison. There's another thing too, we could examine the hydraulic one more carefully. Here is the hydraulic theory written out again, where Q here is the flux, and here's the flux term. And if we plot the flux for certain values of A, we find that the flux function as a function of Y is non-convex. And so this means that, well, we'll see what it means. The speed associated with this, of course, is just Q dashed, and a classical shock requires that the speed of the shock lies between the speed at either side of the shock. And so if we try and match that up, this is the gradient of this is the speed. And here's our shock. If we try to join these 2 points, then the gradient of this chord, it's certainly bigger than the gradient of the flux function there, but it's also bigger than the gradient of the flux function there. So we can't have a classical shock of that full height. In fact, the best we can do is we can join it as a tangent to the flux curve at this particular height. And then from here onwards, in fact, the speed is decreasing, the gradient's decreasing, so we would expect a rarefaction. The higher it was, the slower it went. And so this would say, in fact, what we should have is a partial height shock, but we're joined to the upstream edge by a rarefaction. And here is an initial value, the dotted line. It's been integrated, I think, for 100 times depths. And this is what we see. We see the rarefaction and then the partial height shock. And that line across there is the line predicted by that tangent point. So that's one thing that can be going on. Instead of getting a classical shock, we get this shock rarefaction. The other thing that we can see is we could get dispersive waves. Because y is a constant now, we can integrate up twice actually, and we can get a potential form for the homogeneous equation. Here is our potential form, an expression for y dash squared. Work out the linear wave speeds. And we can get a number of waves depending, nonlinear waves, depending on the form of that curve. The generic case, of course, is that it's got to be positive because it's y dash squared. So we could get periodic waves, finite amplitude periodic waves. If we have a single minimum, then we can get this homoclinic orbit, and the homoclinic orbit gives us a solitary wave. If we have 2 minima of the same height, then we can get a heteroclinic orbit. And of course, that gives us a kink soliton. And a fourth thing that can happen with this problem is that if we have 1 minimum and that curve makes it to the origin for y equals 0, then we can have an intrusion, which is a flat region plus a front that goes down to the wall. Okay, so what can happen? Well, if we solve for a case where there would have been a shock in the previous case, then what we get instead in the convex region is we get a dispersive shock wave. Here's the dispersive shock wave. I won't go into it, but we can predict the amplitude of the leading soliton, or the trailing soliton, leading soliton in this case. You can predict the position of the leading soliton. You can predict the position of the trailing linear edge, and you can predict the wavelength of the trailing linear edge. And here's another example, this time where it's this step where we get it's propagating in the opposite direction. And the theory, I won't go into the theory. The theory is well known. It's a very important theory done by Gennady L. And he showed you how to write down an ODE, which if you integrated it up, gave you the local wave number at every point. So I won't go into that. His theory only applied in the convex region. So what happens in the non-convex region? So in the non-convex region, that was sorted out by Gavin Esler and a student at UCL. And what they showed was that what happens is in the non-convex region, there'll always be a kink soliton. And there's a unique kink soliton given your upstream value of y and your value of a. And that takes you up to a unique height, but that always takes you into the non-convex region. And now you can apply Gennady's theory to that. And so again, you can predict where the kink soliton will be, you can predict the height the kink soliton will come to, then you can predict the leading soliton here or the trailing soliton and the leading linear wave and its wavelength. And this is a comparison between the analytical predictions and the long time, very long time, 30,000 dispersive equation integrations. And in this is another parameter regime. Here we get the kink soliton plus a rarefaction. So you get this in the full problem. So let's go now to the quantidynamics, not the long wave equation, but the full quantidynamics, the equivalent of the Euler equations for this problem. And in fact, you get most of this. Here's the prediction of where the jump should be. Here is the prediction of what the profile should look like of the dispersive shock wave. Here is the prediction of the depth of the dispersive shock wave, but we've only got this depth, but this is deepening. And if we could integrate this long enough, then we believe it will eventually get down here. But the trouble is you've got all these things here that you have to resolve. And in this problem, you're not got a spectral method. You're putting points on each of on this line. It's a contour. You get, here's one with a kink soliton leading into a dispersive wave frame. And here it's actually, of course, the approximation isn't bad. Captures the depth of the shelf we heard about yesterday, captures the depth of the shelf, and it captures the amplitude of the first wave. Oh, and here is another one. Okay, so the final thing is, let's go back to this thing we didn't really get right, and let's see if we've got an idea of what's going on now. Let's see, we're saying in the positive side, it looks like we have a shelf plus a rarefaction. In the negative side, we have a shelf, a rarefaction, a shelf, and then an intrusion. And a current student at UCL is looking at this problem. He can reproduce this in the dispersive equation, because this is quantidynamics compared with hydraulic theory. He can reproduce it, and then theory that to the left, it looks like we have got this rarefaction leading to a constant width current and then leading to an intrusion. And on the right, two things can happen. In the wide source case, which is really when we expect the equation to be most relevant, then we get one of those free waves. We get partial soliton on this side, and that gives us the joining to the shelf. It gives us two boundary conditions, which then match across to the demand that this is flat on this side, gives us one boundary condition, and that gives us a unique solution. So it looks like we can capture this shape from the dispersive wave theory. For narrow sources, something strange seems to go on, but it seems the dispersive theory still seems to work, strangely enough. And what it seems to give is it gives a complete soliton and a jump across in Y across here. And you might wonder, how can you have a jump in a dispersive equation? But there's a jump in the source function as well. And so because the forcing has a jump, it turns out the solution can have a jump because the highest order derivative is balanced. So I'll leave it there.